Right, these are some Jordan normal form examples which someone requested for the 2x2, 3x3 and 4x4 matrices. The 4x4 matrices, I could barely find any examples, so I had to create an example, which took forever, it took hours actually, but it's there and it helped me quite a lot actually. If you don't know what this is, then I'll have a link here on how to work them out. So this is the 2x2 example. We've got a 1, 3, 4, 2, nice simple matrix, and we find the characteristic polynomial, which is x minus 5, x plus 2. Now we want to find the kernel of this matrix A minus 5, which we can do like this, which as we can see is a nice simple, we can put the x over here, and we get x is y, so 1, 1. The next one, we have the A minus A plus 2, and we can see here that x is 3x is minus 4y, so we can substitute x is 4 or something somewhere. We get 4 minus 3. Again, it's a nice simple kernel. I will put a link below for there's some good online matrix multipliers and kernel finders as well, which I found very useful and I did use quite a lot. Not in this case, so this is a nice easy one. And then what we do now is you can put them together, so we can either have 1, 1, 4 minus 3, or we can have 4 minus 3, 1, 1. And as from the last video, you can see all it does is it reverses the way it's done. So P inverse AP, and like that. Yep. Now for the 3x3 example, a little bit more difficult. We've got 3, 3, 4, 4, 4, 2, 5, 3, 2. Not many negatives there, but never mind. That should be a cubed. Now we want to find the change of basis for this. Again, we've got this x minus 10, x plus 2, x minus 1 is the characteristic polynomial. So this is going to be a nice simple one. So we find it for x minus 10 first, the kernel of this, and we write it out in this form here, which I find useful. And let's see, how are we going to go about solving this? If we do this minus this, we've got 12x minus 12z gives us x is z, and from x is z we can work out that y is also the same, so we get 1, 1, 1. The next one, we do the a plus 2, so this minus 2, plus 2 even, and then put it in this form here, and we can work out that the kernel is minus 3, 1, 3. I'm not going to bore you on how to work that out. Again, it's just rearranging. You could probably do, that's a bit useless having two of the same, but that's how it's worked out. I multiply this one by 2 and subtract it from that. That'll give you what x is in terms of y, and then you can put the x in terms of y up here, and then work out what the z is from that. Oh, what's that? Right, now we've got the last one, which is the a minus 1. So again, we do this. From this we get the equations here. This is how I do it anyway for the kernel. And then we can, what should we do for this one? We could subtract any of these from each other to get rid of the y's, which give us x in terms of z. And then once you've got x in terms of z, you can put them into any of these equations and it'll give you x or z in terms of y. So we can work this equation, this vector out here. And now we just want to stack them together. And again, this will give you a p inverse AP is which gives you 10 minus 2, 1. Now we get onto the tricky one. This is I think is the most useful. I had to create this, it took forever. But it ended up being this. 1 minus x to the power 4. Isn't that a nice characteristic polynomial? Right. So this is the big matrix, and this gives us the characteristic polynomial here. So the first thing I want to do is find the kernel of a minus 1. It doesn't matter which way around you do the inside of the bracket. It could be 1 minus x or x minus 1. In either case, x is 1. So let's do the first one. It gives us this matrix here. I hope you can read that. And then we get these equations here. We can see we've got x in terms of y here. So y is 2x. So in this case, I start substituting in x is 1, and it will give us what y is there. And we can work out what w is, because we've got x and y, haven't we? and then because we've got all of them now, we can work out z as well from either of those, and this gives us this equation, this vector here. The next one is the a minus 1 squared, so we're going up again, and this gives us this matrix here, and then we can multiply it by the xyz vector, which is what I do, to give us these equations. Got z in terms of w, put, no, I wouldn't put it in there, but it will give you these vectors here, 1, 0, minus 3, 6, and 1, 3, 0, 0. And I did that using a online kernel finder, and it works perfectly, because it does take some time doing it for a 4x4. So, as you can see, we've got this here and this, and if we look at this previous one, I'm going to say that this extends, I'm going to recall that, this one here, because I think it's most like that one, other than this one. So now we have to find it for the cubed. Kernel of that cubed, this here, these equations, if you work them out, we'll use the online finder, you get these vectors here, and we can see that we've clearly extended. So I'm going to call that one to here, 1006, and this one to there, because they are the same, and this is our new one here, 0010. And now we do it for the last case, which is to the power 4, and this gives us a 0 matrix. So now we can put whatever we like as the last one, but it needs to be linearly independent, remember. So we can put a 1 here and a 0 here, because that would just be the same as this. So I put, we didn't have many W's, so I put a W as 1 down there. Right, now what we want to do is the tricky, messy part. These are what we've got so far. The first time we did it, we got this, then we extended it and we got an extra one, extended again, we got an extra one, extended again, we got another one. So I've tracked this, I've decided that this is the same as, it's going to be that, it's going to be that, it's going to be that. And I've decided that this one, well, that one stays the same all the way through, as does this one to there. So now what we want to do is we've got 4 vectors, and we want to change them using this. So we're going to let the last one equal this, so that can stay as it is. The next one, we want to change the third one by multiplying this by the a minus 1 matrix, and this will give us a new one here. And then once we found that, we'll multiply that by the a minus 1 matrix to give us a new one here, and then we'll do the exact same again to give us a new one here. So we're multiplying, remember, a minus 1 by this, so this times that, which gives us this. They're nice easy ones to do, because the 1 just goes down there, minus 1, minus 3, 1, 0. So this is our new one, so this replaces this. Now we want to do exact same again, but using this matrix, that, so that times that, and this gives us 0, 1, 1, minus 2. So this replaces this. And now we want to do the exact same again for a final time to replace this one by something. So we get this times this, which is this times this, gives us 1, 2, minus 1, 2, which is actually the one we started off with. So that's quite pleasing, really. And now we can just stack them up in what we found. So this is what we changed the first one to, this is what we changed the second one to, and the third. The 4 stays as it was, remember. This gives us P inverse AP, which gives us this matrix here, which is what we wanted, because you've got the eigenvalues down the middle, and it repeated the eigenvalue of 1 4 times, so it should have 4 ones, and then just above that we've got the 1s as well. I hope that was useful.